In this problem, we will use our chemical potential framework to develop or derive equations that you have previously seen that describe the behavior of mixtures that are at equilibrium in both the liquid and the vapor state. And so in this problem, we're told that we're dealing with carbon dioxide and water, and that the Henry's law constant for carbon dioxide and water, which is H, is equal to this value here, 1587 bar. And what this problem wants us to do is it wants us to estimate the mole fraction of CO2 in water at these conditions. We're told to treat the vapor phase as an ideal gas and the liquid phase as an ideal solution, right? And we're also asked to determine the mole fraction of CO2 that's in the water phase, okay? All right, and for this problem, we're also given these parameters for the Antoine equation for water. In fact, this should say water. Okay? All right, and so based on the information in this problem statement, I want you to kind of sketch out a sort of diagram of what's going on in this system. And so based on this problem statement, we could sketch out our system like this, in which we have some sort of mixture which has a liquid phase in which the mole fraction of CO2 in that liquid phase is xCO2 and the mole fraction of water is xW. And we also have a vapor phase as well with the mole fractions of CO2 and water in that vapor phase. Now our goal for this problem is we want to calculate the mole fraction of CO2 that's dissolved in the water. And we're told that the pressure is 21 bar, the temperature is 298.15 Kelvin, and we're also given this Henry's law constant, which we'll talk about why it's useful later on. Okay? And so in order to do this calculation, we first need to make some assumptions about our system. Okay? And so the first assumption we're going to make is one that's told to us in the problem statement. Specifically, that we need to treat the liquid phase as an ideal solution. Right? We're told to do that in the problem statement, but at least the justification for that has to do with what concentration of CO2 we expect in the liquid phase. Now, as you may remember from Mass and Energy Balance 1 or previous courses, CO2 actually isn't that soluble in water, right? You only get small amounts of it that like to stay in water. And so in general, when we think of CO2 in water, we typically think that there's only a dilute amount of CO2 in water. Okay? Right? And why that's important, in order to kind of understand what's going on, we could have this sort of diagram in our mind when it comes to dilute solutions. And so in this diagram, or this illustration, what we have is a mixture or solution in which the triangles represent the solute and the spheres represent the solvent. And so for the most part, the system is dilute in the solute, right? So a solute molecule is typically surrounded by a lot of solvent molecules, right? Usually only sees the solvent molecules. And as we know, in general, when it has to mixtures, when we have the solute and the solvent, there may be some sort of non-ideal interaction going on. But if we consider the entire solution, for the most part, most of the solution is just solvent molecules. And so most of the interactions that are going on are just between other solvent molecules. The interactions between solute and solvent, they're few and far between. And so in general, right, when we think of an ideal solution, the assumptions that we take are that the interactions that are going on in the system, the interactions between the different constituents are basically the same, right? And that the molar volume of the constituents are similar. When we're dealing with dilute solutions, because there are so few solute molecules, the mixture basically just acts as, just the solvent, right? And so we mostly just have solvent interactions going on, or solvent-solvent interactions going on, and solvent-solvent volumes that we need to consider. All right? And so because there's a dilute amount in the solution, what we would say is that the excess Gibbs energy involved in our mixture is basically zero, right? We don't really need to worry about those non-idealities. And so when dealing with a mixture, if you see the word dilute, really what you should take that to be is it's a sign that you could treat your mixture as ideal, as an ideal solution. All right. The other assumption we're going to make is that our vapor phase is an ideal gas mixture. Okay, and we'll see where that assumption comes into play. All right, and so what we want to do is we want to develop some sort of model that allows us to relate or calculate the mole fraction of CO2 that's dissolved in the water phase. Okay, and so to approach this problem, we're going to take we're going to use our chemical potential framework, and we're going to follow the same steps that we applied in the previous problem. And so the first step we're going to take is we're going to define our equilibrium criteria. And so, in our system, we're dealing with vapor and liquid in equilibrium. And so in order for those phases to coexist, the following need to be true. The temperature of the vapor phase needs to be equal to the temperature of the liquid phase. And at the temperature at which that occurs is known as the saturation temperature. The pressure of the vapor phase is equal to the pressure of the liquid phase. The pressure in which that occurs is known as the saturation pressure. Right? And the final criteria, the chemical potential of species I in the vapor phase needs to be equal to the chemical potential of species I in the liquid phase. Right? So this applies for either water or CO2. Right? So same sort of criteria we used before. Our second step is now we need to define our chemical potential formulas. For the vapor phase, if we're talking about the chemical potential of some species I, so either CO2 or water, that chemical potential is going to be a function of the temperature, the total pressure of the system, and also the mole fraction of that species in the vapor phase. That chemical potential is going to be equal to some sort of standard state chemical potential, which is defined as a function of temperature and also defined in terms of some sort of standard state pressure. Right? And then we have an additional term that accounts for the really the entropy of mixing. Right? And so when dealing with ideal gases, as we saw before, our chemical potential looks like this. Okay? Now for the standard state chemical potential, we're going to define it in terms of the pure vapor of species I. Okay? And for this partial pressure here, we could also write that directly in terms of the mole fraction. And so we'll write our standard state chemical potential for the pure vapor, so I'll put a P there. That's at some temperature and the standard state pressure. And then we have RT ln of Yi total P over P naught. For the liquid phase, our chemical potential is written like this. T, P, and now Xi, because we're dealing with a liquid. And so similar to the vapor phase, for the standard state chemical potential, we're going to write it for the pure liquid species. Pure I species liquid. And then we have our entropy of mixing term, which is for liquid, RT ln of xi. Right? So those are our chemical potentials for the vapor and the liquid phase. We now move on to our third step, which is apply our equilibrium criteria. Okay. All right, and so when applying the equilibrium criteria, I'm going to break this problem into two parts. We're first going to apply the equilibrium criteria for water, and then we're going to do it for CO2. Right? So even though in the end we want this value, we need to approach this systematically, right, in order to get develop the equations that we need. Okay? All right, so I'm going to start with water. And for water, when we wrote our chemical potentials, we had some sort of standard state pressure that we need to deal with. And so the standard state pressure I'm going to use for this problem, and so this will apply to both the water and the CO2, is I'm going to let our standard state pressure be whatever the saturation pressure is for pure water at some temperature. Okay? And so since we're letting P naught be equal to P sat for water, that means that our temperature is also going to be the saturation temperature. Okay? All right, and so at these conditions, we'll take a look at the chemical potential of water in the vapor phase, so we'll have the standard state chemical potential of pure water in the vapor phase at T sat and P sat W. And then we have our RT ln mole fraction of water over P sat W. Okay? That's for the vapor phase. For the liquid phase, we have our standard state chemical potential of water, pure water in the liquid phase at T sat and P sat plus RT ln xW. Okay. All right. One thing I want to point out is that, by definition, the standard state chemical potentials correspond to just the molar entropy, or molar Gibbs for pure water. So that's true for the vapor state and also for the liquid state. Okay, in any case, we have our chemical potential equations, and so I'm going to set them equal to one another. So what we have is this. So I'll write out this to emphasize W P sat W. That's equal to this plus RT ln of xW. All right. So this is our chemical potential equation. All right. To simplify this down, what we have to remember is that at the saturation pressure and temperature, if we go back to our previous chapters, we learned that at those conditions, what is true is that the molar Gibbs energy of some species in the liquid phase is equal to the molar Gibbs energy of some species in the vapor phase. Right? All right, and so what that means, consequently, is that our standard state chemical potentials for water in both the liquid and the vapor phases, these are equal to one another, right? Just by definition. And so, if we take this equation, and I'm just going to copy it to a new page. If we take this equation, because this and this are equal, and they're on both sides, we could cancel them out. Okay. We also have RT on both sides. Those cancel. And those ln's, we just take the exponential of both sides, and we could get rid of them. And so, if we rearrange the equation, what we get is the following relationship. So our partial pressure of water in the vapor phase, which is just the mole fraction times total P, is equal to the mole fraction of water in the liquid phase times its saturation pressure. This equation you've seen before. This is Raoult's law. Right? So this is the same Raoult's law that you used in both MEB1 and MEB2. Right? And this is how you derive it, through chemical potentials. And so with Raoult's law, I just want to remind you, one of the main assumptions is that you assume ideal solution behavior.